Hey, on this video we are going to go over the graphing motion introduction notes for physics. So the reason we use motion graphs is that they are a great way to convey a lot of information of real-world events in a compact form. So for instance, this is a set of all three of the motion graphs we're going to be looking at, and there's a whole lot of information packed into this picture that it would take me a page of writing to explain to you about how it's moving, how much time it went for, how far it went, how fast it went, its acceleration rate. And you don't want to read a whole page of information, but instead we can just easily analyze each graph and pull information off of that. So that's what we're going to be working on in this unit, is being able to analyze and construct these graphs. There are three graphs we're going to look at. The first is a position time graph. This goes by a couple other names, such as distance time graph or displacement time graph. The second is a velocity time graph, and then the third is an acceleration time graph. So today we're mostly going to focus on position time graphs. Before we go over position time graphs, though, I want to look at a few definitions just to make sure that we're all on the same page with this. So first off is the term displacement. You heard me say that on the last slide when talking about position graphs. They're also called displacement time graphs. Displacement means the distance between where an object started moving and ended moving. So for instance, if you have a person on a sidewalk and they walked back and forth on the sidewalk several times, their total distance, let's say they started at a spot of 0 meters and ended over here at 10 meters when they turned around, their total distance traveled, you would calculate, okay, how many times did you walk back and forth? So we walked 10 this way, and then I walked 10 more that way, and then I went 10 more back to here. So I walked a total of 30 meters for my distance. However, for displacement, we're just looking at where you started versus where you ended. So he's ended 10 meters from where he started, so he only has a 10 meter displacement. All right. Next definition is position. That's simply saying where the object's located. So like a position time graph is telling us where it's located at that point in time. So for instance, if this guy starts off at 0 meters, that's his position in the start, and he ends at a position of 10 meters. Our velocity is the speed as well as the direction of an object. Speed is simply how fast you're going, and then velocity is going to include then how fast you're going as well as which way you're going. Then acceleration is the rate at which your velocity of an object changes. So this could mean your speed is changing or your direction is changing to be undergoing acceleration. Also know that for acceleration in physics, that means speeding up and slowing down. So commonly when you are driving a car, you think of acceleration as speeding up and then deaccelerating as slowing down. But in physics, acceleration means both. We don't typically use deacceleration. You may hear it, but it's technically the incorrect thing to say. So this term means speeding up and slowing down, and we don't use the term deacceleration. Don't do that. All right, and lastly, slope. We're going to be analyzing the slopes of the lines on the graph, just like in math class, and that's just your steepness of the line. All right, let's move on to position time graphs. So a position time graph represents the location of an object during a segment of time. So here we have a nice little position graph. You'll notice on the x-axis is the time. It's typically going to be measured in seconds, not to say it can't be in hours or minutes or something else, but you'll most commonly see seconds. And then on the y-axis is the position or the distance or displacement. And that's typically going to be measured in meters, but you may see kilometers or other units of distance as well there. For the motion of the object in a position graph, we can analyze it by looking at the shape and the slope of the line. So let's look at this one right here. Let's say that this is a person walking again, like on the last example of the guy walking back and forth. So they start at 0 meters. So let me draw that real quick. So he starts here at 0 meters. He walks for 5 seconds and he ends up 4 meters from where he started. Then at this point here, he turns around and he walks backwards then and goes past where he started all the way past that and ends up, it says -4. So he's 4 meters over this way, and then he just stops moving. And I can know all of this because I'm analyzing, as I'm saying this, the shape and the slope of the lines and what those mean. So let's break that down now. So first let's look at the slope of the line, and that's going to tell us the velocity of our object. If we have a negative slope, that means we have a negative velocity, meaning we're going to be also going in the negative direction. Some people will call this backwards. Typically in physics, we set to the left as the negative direction, as well as down as the negative direction if we're going vertical. Then if we have a positively sloping line, we're going to have a positive velocity, meaning we're going to be going in the positive direction or forwards. And typically we say this is to the right or upwards if we're talking about vertical direction. Then if we have a slope of 0, it means we're not moving. And here I've got the slope formula written out for you in several different ways. Most students are going to pick rise over run as their version to use because that's what you most commonly used in math class. So make sure you're able to determine the slope of a line because we're going to use that quite a bit when analyzing our graphs. So looking at this graph here of the example we were previously working on, in this first section from 0 to 5 seconds, you have a positively sloping line. If we were to find this slope here, it would give us how fast we're going, and then the fact that it's positive tells us we're going forwards. If we did the second section, we would know that it's since it's sloping downwards, it's going in the negative direction. If we were to calculate that slope, it would tell us how fast it's going as it's going in the negative direction. And then last, from 10 to 15, it would not be moving. So now let's look at an example and see how you're doing with this so far. So first up, we're going to calculate the velocity from 0 to 3 seconds. And y'all have this same graph on your guided notes to work off of. So we're calculating the velocity from 0 to 3 seconds. So we're going to look at the slope of the line from 0 to 3 seconds. So here we have a rise over run is what we're going to do. And our rise goes from 0 up to 6. So 6 minus 0 is just 6. The units for that rise are going to be meters. It's whatever units are on your y-axis. Typically, again, it's going to be meters. And then your run, we're just going from 0 over to 3. So 3 minus 0 is just 3. And then our units are going to be seconds because that's what's on our x-axis. So then we divide 6 by 3, and that's going to give us 2 meters per second. So we're going a positive 2 meters per second for those first 3 seconds. For question 2, we're calculating the velocity from 5 to 8 seconds. So now we're looking at this line right here. And again, we're going to do rise over run. This time we are ending for the rise at 3, and we started at 6 up here, and we're ending at 3. So we're going to be dropping negative 3. And our run from 8 minus 5 is 3 seconds. So negative 3 meters divided by 3 seconds is negative 1 meters per second. So our velocity there is negative 1 meter per second. So we're going in the negative direction at a rate of 1 meter per second. All right, and then what direction, for number 3, what direction is the object moving from 0 to 3? I already said that one, but we are going in the negative direction. All right, and then number 4, during what time segment is the object not moving? So for not moving, you are looking for those horizontal lines. So our first horizontal line is from 3 to 5 seconds. And then again, we have one from 8 to 10. So in this case, there are 2 of them. So again, when you're looking for not moving, you're looking for horizontal lines. Next up, we're going to look at the shape of the line and what that tells us. We'll see 3 shapes. First is a diagonal line. This is going to tell us constant velocity, like we just worked out with slope. When we find the slope of a diagonal line, that's telling us that it's maintaining that velocity for that duration of time. So if you're just quickly glancing at a graph, whenever you see a diagonal line, you'll know that it's going at a constant velocity. For curved lines, they're going to tell us the object is accelerating. Again, accelerating can mean speeding up or slowing down. If our curve is increasing in steepness, that means your object's going to be speeding up. So for instance, like this curve is flatter in the beginning and gets steeper as it goes up. That means this object here would be speeding up. Versus if it's decreasing in steepness, it's going to be slowing down. So for instance, this is really steep in the beginning and gets flatter towards the end. This object would be slowing down. And then lastly, if we have a horizontal line, which would mean a slope of 0, our object would not be moving. All right, now we're going to go through this set of 9 graphs that are on your sheet, and we're going to talk about whether they are going in the positive or negative direction, if they are speeding up, slowing down, or constant velocity, or not moving. So first with graph A, we have a diagonal line here. So it is positively sloping and headed up on the graph as you read it from left to right. So that means positive direction. So I'm going to write a plus sign to represent positive direction. It is also a diagonal line. So if we look back at our previous notes, we know a diagonal line means constant velocity, that it's maintaining the same velocity for that entire time. So I'm going to write CV for constant velocity. For the second graph, to determine whether it's going positive or negative direction, we're looking at which way our line is sloped. So in this case, our diagonal line is sloping downwards, meaning it's going to go in the negative direction. It's also a diagonal line, so just like graph A, that means it's going at a constant velocity the whole time. Now with graph C, we have a curved line, and it's headed up on the graph, and when it's headed up or positively sloping, it would be going in the positive direction. And in this case, we want to now know if it's going speeding up, slowing down, or constant. And with the curved line, we know it's not going to be constant velocity, and it is accelerating. So to determine if it's speeding up or slowing down, we're looking at the steepness, and we can see it's really flat in the beginning and gets steeper towards the end. So that would mean it's speeding up, and we're going to do an up arrow to represent speeding up. Now for graph D, we have another curve. This time the curve's headed downwards. That's going to mean it's going to go in the negative direction. And then we're going to look at whether it's speeding up or slowing down. We want to look at how steep the steepness of the line, how it changes. It's steeper in the beginning and flatter at the end. That would imply that this object is slowing down. All right, for graph E in the middle here, and again, another curve. It's headed up on the graph, so that would be positive direction. And then our line is a curve, so that implies acceleration. In this case, it's steeper in the beginning and flatter in the end. That would imply that it's slowing down. And then our last curve here for graph F is headed down on the graph, so it would be the negative direction. And then it's getting steeper as it goes through this curve, which would imply speeding up. Okay, so let's look back at these graphs real quick and recap. So the ones that are going positive direction, so A, C, and E are all positive direction. You'll notice that all of those lines are headed upwards on the graph or positively sloping on the graph. All of them that are going in the negative direction, so B, D, and F, are all headed down on the graph as you read them, or are negatively sloping. So that implies negative direction. Your diagonal lines are the ones that are constant velocity. And then the lines that are getting steeper at the end, so this is steeper than it was in the beginning, and then this is steeper than it was in the beginning. Those would be speeding up. These, for D and E, they were slowing down because they were getting flatter towards the end. Okay. Now to finish off this set of graphs, the last three here, it's hard to see G, it's actually a line on the x-axis. And then for H, it's above the x-axis, and for I, it's below the x-axis. All of these are horizontal lines, so I hope you're already telling yourself that all three of these are not moving. Okay, they're just showing you that, hey, this is sitting at like the starting point, this is sitting somewhere above the starting point, and this is sitting somewhere below the starting point. But all three of those are telling you that the object is not moving. All right, let's move on to our last example, and this graph is also on your guided note sheet to look at. So we're going to put all the pieces kind of together now. So we're looking first at which time segment or segments is the object doing these things. So for number one, not moving. What are we looking for to show not moving? We're going to be looking for horizontal lines. Where do we have a horizontal line on this graph? From 4 to 6 seconds. So my answer for number one is 4 to 6 seconds. Number two, when are we moving in the positive direction? Think to yourself, what am I looking for to show positive direction? I'm looking for it sloping positively or going up on the graph, and it's doing that in this case from 0 to 4 seconds, as well as 6 to 8 seconds. For number three, when are we moving in the negative direction? What are you looking for to determine that? You're looking for the line to be headed down on the graph or sloping negatively. And it is doing that at the very end of the graph from 8 to 10 seconds. All right, now for number four, when are we slowing down in the graph? So what are you looking for slowing down? You want to look for a curve, and you want to look for it to get flatter or less steep towards the end of that curve. And it's going to be doing that from 6 to 8 seconds. So this curve right here is very steep in the beginning and then begins to flatten out as it reaches its peak at 8 seconds. And then for number 5, speeding up, we also, again, are looking for a curve. So that's going to leave us with 8 to 10, and it's flat here and gets very steep towards the 10-second mark. So that is our answer for number 5, from 8 to 10 seconds. And then lastly, has a velocity of 2 meters per second. So if it's maintaining this velocity, we're looking for a diagonal line that has a slope of 2 meters per second. For this particular graph, we only have one diagonal line. If you had multiple diagonals in your graph, you would just find the slope of each one. In this case, we only have one, so all you really want to do is check the slope of it to make sure I'm not trying to trick you, and the reality is like it never does this. So we're just going to check the slope of this real quick. We know our rise here goes from 0 up to 8 meters, so our rise is 8 meters. Our run goes from 0 to 4 seconds, so our run is 4 seconds. And divide 8 by 4 gives us an answer of 2 meters per second. So then that checks out. When it has a velocity of 2, would be from 0 to 4 seconds, and I'm not trying to do any kind of trick questions here. All right, that is all for this set of notes. Let me know if you guys need any help.